Probably it's the most exciting moments of the life when you receive signal from the planet. A great disappointment when it stopped transmitting and you could not do anything else.
In the annals of space exploration, few narratives are as enigmatic as the Soviet Union's foray into Mars exploration. After achieving significant milestones in space, the Soviets aimed their sights on the Red Planet, hoping to mark another first in space conquest. However, following a seemingly successful landing, there came an unanticipated silence, a mystery that would remain unsolved for decades. This video delves into the captivating tale of the Soviet Mars landing, shedding light on the technological triumphs, the unforeseen challenges, and the persistent questions that still hover around this audacious mission. The mid-20th century bore witness to one of the most intense periods of geopolitical competition, the Cold War. Underlying the political and military tensions between the USA and the USSR was a battle of technological supremacy, manifesting most prominently in the race to explore space. This space race symbolized not just scientific advancement, but national pride, ideological dominance, and the projection of military might. While both superpowers had their sights set on conquering the final frontier, the starting lines were different. In 1957, the Soviets took an early lead with the launch of Sputnik 1, the world's first artificial satellite. This unexpected Soviet achievement caught the American public and its policymakers off guard, pushing the U.S. into immediate action. The response was swift: the formation of the National Aeronautics and Space Administration, NASA, in 1958, and an accelerated focus on space exploration. However, Soviet achievements continued to pour in. The USSR not only sent the first human, Yuri Gagarin, into space in 1961, but also marked significant achievements like the first woman in space, the first multi-crew mission, and even the first spacewalk. Each accomplishment heightened the competitive spirit of the space race and pushed the U.S. to double its efforts. America's answer came in the form of the Apollo program. In 1969, it achieved the historic feat of landing humans on the moon and safely returning them to Earth, effectively leaping ahead in the race. Yet it wasn't just about the moon. Both nations also eyed other celestial bodies. This pursuit gave rise to various sub-races. These sub-races focused on diverse objectives, from exploring specific planets like Venus and Mars to developing technologies that could support longer-duration space flights and establish a human presence in space. While the term sub-races might suggest secondary importance, the technological and scientific strides made in these endeavors were in no way lesser. For instance, as the USA aimed for the moon, the USSR worked on robotic missions to Venus, and later, as noted, Mars. Though the space race was born out of rivalry, it fostered massive technological advancements. The rapid development of rockets and satellite technology had repercussions beyond space exploration. The progress made in understanding human health and survival in space paved the way for modern astronautics. It also accelerated advancements in areas like telecommunications, materials, science, and computer technology. The fierce competition gradually evolved into collaboration, most notably symbolized by the Apollo-Soyuz test project in 1975, where an American and a Soviet spacecraft docked in space. This event was emblematic of the thawing relations between the two superpowers and set the stage for future collaborations in space, like the International Space Station program. The space race was much more than just a bid to reach the moon. It was a testament to human ambition, with celestial bodies like Venus and Mars also featuring prominently in the competition's narrative. While the United States made headlines with their lunar missions, the Soviet Union cast its eyes further afield, focusing its gaze on the elusive red planet, Mars. Mars, often dubbed Earth's sibling planet, has long captured human imagination. With similarities in its axial tilt, rotational period, and speculated history of water and vegetation, the red planet promised a wealth of knowledge waiting to be uncovered. The allure was not merely scientific. Mars, with its potential for harboring extraterrestrial life and its distant allure, represented a greater challenge, an emblem of unparalleled exploratory triumph. The Soviet Union's journey towards Mars was characterized by both ambition and adversity. The genesis of their Mars program can be traced back to the early 1960s, parallel to their lunar exploration. However, early endeavors like the Mars 1M probe in 1960 faced challenges, failing to even reach orbit. Subsequent attempts, like the Mars 2M, met with similar ill fate, being destroyed during launch. These early setbacks, while disheartening, were invaluable lessons for the Soviets. They highlighted technological gaps, offering insights that would be crucial for subsequent missions. As the 1970s dawned, the USSR's Mars exploration program began to crystallize with more refined goals and sophisticated technology. Recognizing the significance of 1971, a year of conjunction when Mars and Earth would be in minimal distance from each other, the Soviets geared up for their most ambitious mission yet. Such moments of conjunction, occurring once every 15 to 17 years, were vital, reducing the energy required for interplanetary flights, enabling heavier payloads and increasing the chances of success. Mars 2 and Mars 3, launched in 1971, encapsulated the Soviet Union's renewed vigor. These missions were not just attempts to reach Mars, but were comprehensive in nature, consisting of orbiter modules and attached lander modules. The design showcased the accumulation of Soviet space knowledge: spherical landing capsules, conical braking shields, parachute systems, and retro rockets. Weighing 4,650 kilograms, these spacecrafts were titans of their time, designed to endure the challenges of interplanetary travel. At the heart of these missions lay the Prop-M rover. No larger than 5 kilograms, this rover symbolized Soviet ingenuity. Designed with a square-shaped body, the robot was meant to traverse Mars's dunes with ease, supported by skis providing necessary clearance. Equipped with advanced detection bars, it was built to navigate Mars's rugged terrains, avoiding rocks and potential pitfalls. The rover, connected to its lander by a 15-meter cable, was a herald of the potential for robotic exploration. The thought that this tiny machine could relay Martian soil's strength and density back to Earth was both exhilarating and revolutionary. However, the journey to Mars was riddled with challenges. While the Mars 2 faced landing malfunctions, crashing onto the Martian surface, Mars 3 etched its name in history as the first spacecraft to achieve a successful soft landing on the planet. Though the rover's operational time was tragically short, the partial data it sent back was groundbreaking. A fleeting glimpse of the Martian surface, even if just a gray background, was a testament to the mission's partial success. The USSR's Mars missions, especially the events of 1971, encapsulated the dual nature of space exploration. The euphoria of achievement, coupled with the unpredictable nature of extraterrestrial endeavors. While Mars 3's sudden loss of contact post-landing was a poignant moment, it didn't detract from the fact that the Soviets had reached a planet that was millions of kilometers away. The Mars 2 and Mars 3 missions, launched by the USSR in 1971, remain towering achievements in space exploration history. Beyond the fame of being the pioneering missions to the Martian surface, their intricate designs and onboard technologies stood as a testament to Soviet engineering prowess and the nation's undeterred spirit in the face of early failures. Initiated against the backdrop of the 1971 Mars-Earth conjunction, these missions represented the pinnacle of Soviet interplanetary ambitions. The spacecrafts, each weighing approximately 4,650 kilograms, were among the heaviest of their time. While their weight indicated the vast amounts of equipment they carried, their modular design showcased an understanding of the vastness and variability of interplanetary travel. Comprising an orbiter and a lander module, the twin missions aimed to examine Mars both from its orbit and directly from its surface. The orbiter's primary task was to image the Martian surface, study its atmosphere, and relay data from the lander to Earth. To accomplish this, the orbiter was furnished with a suite of scientific instruments. Phototelevision cameras provided imagery, complemented by infrared and ultraviolet spectrometers that analyzed the Martian surface and its atmospheric composition. The magnetometers gauged the Martian magnetic field's intensity and direction, and radiometers collected data on water vapor levels and atmospheric temperature. The lander, on the other hand, was where the real excitement lay. Housed within a spherical casing, it was designed to survive the hard impact if its soft landing systems failed. Encased in a conical braking shield, the lander's descent involved a meticulously planned sequence: aerodynamic braking by the Martian atmosphere, parachute deployment for initial deceleration, and finally, a set of retro rockets to ensure a gentle touchdown. One of the most innovative features aboard the lander was the Prop M rover. This tethered mini-rover, no heavier than 5 kilograms, was envisioned as the Soviets' eyes and touch on the Martian soil. Its uniquely square body shape, flanked by skis, was designed to navigate the alien dunes. The skis provided the necessary ground clearance, while detectors helped it steer clear of potential obstacles. The 15-meter connecting cable allowed it to venture out from its parent lander, transmitting data back about Martian soil's strength, density, and texture. The mission objectives of Mars 2 and 3 were multidimensional. While analyzing the Martian atmosphere's composition and surface geology was paramount, they also sought to answer the age-old question: did life, in any form, exist on Mars? The array of instruments aboard was tailored to address this query. They attempted to search for potential organic compounds and study the planet's geology, atmospherics, and magnetism to comprehend its potential to support life. While their technological marvel is undeniable, the missions weren't devoid of challenges. Mars 2, despite its promising start, couldn't execute a soft landing and crash-landed on the planet's surface. It did, however, earn the distinction of being the first human-made object on Mars. Mars 3's lander fared better, achieving a successful soft landing and operating briefly before losing contact. In that short operational window, Mars 3 managed to transmit the first-ever image from the Martian surface, even if it was just a gray background. The odyssey of Mars 2 and Mars 3 began on a hopeful note. Launched within days of each other in May 1971, both spacecrafts set forth on an ambitious journey of approximately 200 million kilometers to the Red Planet. This venture, emblematic of the grandeur of Soviet space ambition, was a daunting task that encapsulated the immense technical and logistic challenges of interplanetary exploration. As the twin spacecrafts hurtled through space, they embarked on a series of trajectory adjustments, ensuring that their eventual rendezvous with Mars would be optimal. They sailed through the vast cosmic expanse, relaying back data and gradually closing the distance between Earth and their Martian target. Anticipation grew with each passing day, as humanity stood on the verge of achieving yet another unprecedented milestone. Mars 2, with its grand design and scientific cargo, was set to make history. Yet destiny had other plans. Upon its approach, a malfunction in its systems doomed the lander, causing it to crash onto the Martian surface. Although this misadventure robbed Mars 2 of its primary mission, it inadvertently cemented its place in history as the first human-made object to reach the Martian soil. The focus then shifted to Mars 3, humanity's second shot at unveiling the secrets of the Red Planet. As Mars 3 neared its target, the precision of Soviet engineering became evident. The lander separated from the orbiter, initiating its descent sequence. Aerodynamic braking, parachute deployment, and the thruster's final firing worked harmoniously, guiding Mars 3 to a soft landing on the Martian plains. The touchdown was successful, an event that sent waves of euphoria through the corridors of Soviet space research and across the world. A human artifact had, for the first time, landed and was operational on another planet. Yet this jubilation was to be short-lived. Just 14.5 seconds after the Mars 3 lander began its transmission, the signals went silent. From the cusp of what promised to be a torrent of groundbreaking data, the mission control was plunged into a disconcerting void. The first-ever image transmitted back from Mars was merely a gray background, hinting at the alien world, but revealing nothing concrete. The inexplicable loss of Mars 3 remains one of space exploration's most confounding enigmas. Theories proliferated. Some speculated that a massive Martian dust storm might have overwhelmed the lander's systems. Given the planet's propensity for these raging tempests, it was a plausible explanation. Others conjectured that a design flaw or technical malfunction had abruptly terminated the mission. Given the complex choreography required for the descent and landing, even a minor anomaly could be catastrophic. Yet, amidst the speculation and dejection, the Mars 2 and Mars 3 missions had indelibly stamped their mark on human history. Their journey epitomized the blend of daring ambition, scientific curiosity, and the inherent uncertainties of space exploration. The Mars 3 lander's sudden disappearance remains emblematic of the many enigmas the cosmos holds, mysteries that beckon humanity with the allure of the unknown. The landscapes of Mars, with their russet plains and skyward-reaching dunes, may seem eerily serene from a distance. Yet, this tranquility is often punctuated by one of the most captivating and perilous spectacles in our solar system: Martian dust storms. These maelstroms, much more intense than their terrestrial counterparts, carry with them not only the fine grains of the Martian surface, but also a wealth of scientific intrigue and curiosity. Martian dust storms, in their enormity, can range from a small whirlwind, comparable to the dust devils seen on Earth, to planet-encircling tempests that can shroud Mars in a thick, dusty haze for weeks or even months. Such vast dust storms can obscure the planet's features entirely, transforming the appearance of Mars from the distinct, rugged terrain to a blurry, uniform amber sphere. What sets Martian dust storms apart from their scale, is the context in which they occur. Mars's atmosphere is tenuous, with a pressure less than 1% of Earth's. This means the particles carried aloft in its storms, despite their abundance, have lesser kinetic energy compared to the grains in Earth's dust storms. Thus, while an astronaut on Mars would experience the storm as a hazy fog of fine particles, they wouldn't be sandblasted as one might in an earthly sandstorm. The origin of these storms can be traced to the planet's topography and atmospheric conditions. As sunlight warms the Martian surface, it creates pockets of warm air that rise, creating local low-pressure systems. The thin atmosphere and the planet's surface, laden with fine dust, provide the perfect conditions for these systems to lift the dust off the ground and into the air. Add to this the presence of Mars's towering mountains and deep valleys, which act as channels that guide and amplify winds, and you have a recipe for dust storms that can grow rapidly in size and intensity. The possible connection between these Martian dust storms and the mysterious loss of Mars 3 has been a topic of significant discourse. The 14.5 seconds of transmission from Mars 3 before its abrupt cessation showed a gray background, a potential indication of the lander being engulfed in a dust storm. If a raging tempest did indeed surround the lander, it could have compromised its systems in multiple ways. Dust particles, even if fine, can scatter and absorb sunlight, affecting solar panels' efficiency. They can interfere with optical systems, reducing visibility and disrupting communication signals. Furthermore, if electrostatically charged, these particles might adhere to or affect sensitive equipment. Drawing parallels to Earth, dust and sandstorms can cause substantial interference with communication devices, visibility issues for drivers, pilots, and even satellite imagery. Dust particles suspended in the atmosphere can scatter radio waves, leading to disrupted communications. In a scenario on Mars, with its thinner atmosphere and vastly different electromagnetic environment, the implications of a severe dust storm on a newly landed spacecraft could be profound. Yet, while the dust storm hypothesis offers a compelling narrative for Mars 3's loss, it remains one of many potential explanations. Space exploration, as the journeys of Mars 2 and Mars 3 demonstrated, is fraught with uncertainties. The Martian environment, though seemingly barren, is dynamic and replete with mysteries still waiting to be unraveled. Decades had passed since the last signal was received from Mars 3. The buzz and fervor of the Soviet mission to Mars had faded into the annals of history, with newer missions and discoveries taking precedence in the space exploration discourse. However, the mystery surrounding the fate of Mars 3 remained a tantalizing puzzle for space enthusiasts and experts alike. By the late 2000s and early 2010s, the capabilities of orbital imaging and data analysis had advanced significantly. With these technological strides, a new generation of researchers, primarily from America, decided it was time to reignite the quest for Mars 3. NASA's Mars Reconnaissance Orbiter, MRO, was a pivotal tool in this effort. Launched in 2005, MRO had been armed with a high-resolution camera known as the HIRES, High Resolution Imaging Science Experiment. This camera was so powerful that it could identify surface features as small as a coffee table from its orbit around Mars. Given the capabilities of the HIRES camera, the idea to locate Mars 3's landing site and perhaps deduce its fate became a feasible objective. Aided by the details available about the intended landing coordinates of Mars 3, the American team began their search. The researchers pored over images, comparing them to the expected landing area and any known details from Mars 3's brief transmission. The methodical and meticulous nature of this search was akin to finding a needle in a Martian haystack, given the vastness of the region and the decades that had passed. Yet, perseverance paid off. In 2012, images captured by MRO's HIRES were released, suggesting that the Mars 3 lander, its parachute, and other related debris might have been located. These potential findings presented a cluster of features that were consistent with a successful landing and deployment of equipment, followed by some unforeseen event. The recognition of the parachute was particularly significant. Its peculiar shape and size closely matched expectations and served as a beacon guiding researchers to other nearby hardware. Adjacent to the parachute, a brighter circular feature was observed, which researchers speculated could be the lander itself. Moreover, they identified a darker zone possibly indicating the heat shield's touchdown point and the trajectory taken by the lander. These findings reinvigorated the space community's interest in Mars 3. While the images couldn't definitively explain the sudden loss of communication, they did provide some closure by offering potential visual evidence of the lander's final resting place. The rediscovery was also a testament to international collaboration in the realm of space exploration. An American instrument, on board an American orbiter, had assisted in bringing clarity to a historic Soviet mission. Beyond the satisfaction of locating the Mars 3 hardware, this effort underscored the importance of detailed orbital reconnaissance in guiding and assisting surface missions. The synergy between orbiters and landers' rovers was clearly demonstrated, revealing how the eyes in the sky could serve as invaluable tools for ground operations. As the chapters of space exploration continue to unfold, the rediscovery of Mars 3 is a poignant reminder of the enduring nature of human curiosity. Missions, regardless of their origin or outcome, belong to the shared heritage of humanity's quest to reach beyond our blue planet. The American assistance in shedding light on Mars 3's fate is not just a tale of technological prowess, but also one of camaraderie, bridging decades and nations in the timeless endeavor of exploration. In the unfolding tapestry of space exploration, every mission, successful or not, adds a unique thread, contributing to our ever-expanding understanding of the cosmos. The Mars 2 and Mars 3 missions were no exception. Despite the brevity of their active period and the mysteries that shrouded their operations, these missions left an indelible mark on the annals of space history. The significance of Mars 2 and Mars 3 isn't solely rooted in their technological achievements, though they were considerable for their time. Instead, their legacy lies in their pioneering spirit. They represented one of humanity's earliest attempts to reach out and touch the surface of another planet, an audacious leap into the unknown. The missions underscored the immense challenges that awaited in the quest to explore our neighboring planet. A harsh reminder that venturing into space was fraught with unpredictability. In a world accustomed to instantaneous results, Mars 3's mere 20 seconds of data transmission might appear as an anticlimax. Yet, those fleeting moments were profound. They were the first signals from the surface of Mars, and they gave scientists invaluable insights, however brief. This tiny window opened up a plethora of questions about Martian atmospheric conditions, surface properties, and potential hazards. Even in its silence, Mars 3 spoke volumes. While the Mars 2 and Mars 3 missions did not yield extensive data about the Red Planet, their presence and subsequent loss spurred subsequent missions to be better equipped and prepared. In many ways, they laid down the framework for the risk assessments and contingencies that future missions would consider. They also spurred an international sense of competition and collaboration, pushing nations to explore further, delve deeper, and aim higher. However, the legacy of Mars 2 and Mars 3 is not one without shadows. The abrupt loss of Mars 3's signal remains one of space exploration's enigmatic puzzles. Despite the numerous hypotheses, including the likely Martian dust storm theory, a conclusive reason remains elusive. This mystery serves as a stark reminder of the unpredictable nature of space exploration, where despite our best preparations and technologies, the cosmos often has the final say. In subsequent years, as Mars became the focal point for numerous exploration missions, each new rover or lander that touched its surface was built upon the lessons of the past, Mars 2 and Mars 3 included. The questions they raised about Mars's weather patterns, surface conditions, and potential pitfalls guided the designs and objectives of their successors. The ongoing mysteries of Mars 2 and Mars 3 also emphasize the importance of revisiting past missions. As technology progresses and our understanding deepens, opportunities to reevaluate and glean new insights from old data arise. The American-led rediscovery of Mars 3's landing site, decades after its last signal, underscores this very point. Even missions long past can offer new revelations. As we peer into the future of space exploration, the Mars 2 and Mars 3 missions remind us of the boldness of our ambitions and the fragility of our endeavors. They stand as testaments to humanity's relentless quest for knowledge, highlighting both our vulnerabilities and our unyielding spirit. The mysteries they left behind, still whispered among space aficionados, serve as enduring challenges, taunting and inviting the next generation of explorers to seek answers in the vast expanse of space.